Okay, so this is the last lecture of this mini course, this morning so this is this morning's discussion is based on this joint paper with Florian Theil in GEMS 2022. This morning I introduced and motivated the Arisa-Ortiz model. This is the Arisa-Ortiz Hamiltonian. U is displacement field that takes values in RD. Let's say R3, and sigma is a lattice-valued so-called slip field, which is a function. So it's a function from nearest neighbor edges of the FCC lattice to the lattice vectors. This model is invariant under translations, linearized rotations, and these gauge transformations that correspond to relabeling of the sides of the FCC lattice. This is the way in which average with respect to the Gibbs distribution are defined. So it's 1 over the partition function of the sum over gauge equivalent slip configurations of the integral over the displacement field of e to the minus beta this Arisa-Ortiz energy plus this function which gives a finite energy cost to every dislocation core. I'm denoting, I'm identifying the dislocation cores with the phases where this d sigma is supported. Only since the Hamiltonian is invariant under gauge transformations, only gauge invariant observables. So observables that can be written functions of this specific combination are physically relevant. So the observables used to test breaking of translation invariance and the existence of positional long-range order are these two. These are they can be written as these are gauge invariant, so they can be written as functions of du minus sigma, where in this case sigma is an arbitrary lattice-valued slip field. In this way, where h is a function over edges, which is equal to minus v naught if E belongs to a lattice path from X to a reference point in the exterior of our box. I recall you that we are considering the box with Dirichlet boundary conditions for technical reasons. And the main result, so these two observables play the analog role in this context of 1 minus u squared and 1 minus ux squared and 1 minus ux minus uy squared that were used in the harmonic approximation to test positional long-range order. So the main result is that for any vector v0, non-zero vector v0 in the reciprocal lattice, for beta large enough, the average of these functions is uniformly bounded away from 0 by something of the form 1 minus e to the minus c over beta. So this is really the analog of the result obtained in the harmonic approximation, but in a setting in which the system admits dislocations. So the most important somehow the most important low energy excitations are in fact the dislocations. The specific quadratic structure of the model allows for a very peculiar decomposition of the excitations in so-called spin wave excitations and the dislocation excitations. So they really come in a separate way, in a sense that will be made clear soon. So for those of you who know about the Villain model, this is a sort of vectorial analog or tensorial analog of the Villain model, which is a model introduced by Villain in connection with the analysis of Kosterlitz-Towles on the XY model. So the Villain model is a model in which replace the cosine interaction in the standard rotator model with a sort of sum over images of Gaussian interactions. And this simplifies quite technically the analysis and guarantees an exact decomposition between the also their spin wave degrees of freedom and the vortex degrees of freedom. So the model, this Arisa-Ortiz model is somewhat the analog of that model in our context. So for those of you who know the Villain model, this may be a useful reference model to keep in mind. For those of you who don't know the Villain model and are interested to this discussion, it may be useful to look back at that model in which a similar analysis in a simpler context where the model somehow supports vortex vortex excitations that are somehow a simpler version of the dislocation excitations we have up here. Okay, so the rest of this last lecture is devoted to the proof of this theorem. I should be able to give quite a number of details. I mean, so this will be a bit demanding technically. I mean, I wrote essentially all steps modulo minor technical estimates, for which I refer you to the paper with Florian. But I hope to be able to communicate at least the main logic. And since I will give at the end a version of the slides to Eris, Sarah, and Serena that can post who can post them on the website, you can use this as a guide through the paper with Florian, which is longer. Okay, so first of all, so somehow the going through this proof also shows the kind of ingredients that are needed to treat this kind of model. Some of the ingredients, so somehow I got to this subject discussing a lot with Florian Theil, who is an expert in, among other things, elasticity theory. He comes from a background in variational analysis, and so somehow this is a meeting point between my competencies in lattice statistical mechanics models and cluster expansion, and his expertise in elasticity theory. Somehow I learned from Florian and literature on the subject that a very important tool in this context is discrete exterior calculus. So this is actually something that also people working in lattice gauge theories know well. I didn't know well this subject before studying this problem. So let me introduce some basic notions that are needed, that will be needed in the following. So as I told you, I defined this finite portion with the shape of a parallelepiped of the FCC lattice. So this portion of FCC lattice comes with a vertex set, which I previously called V lambda, a set of oriented edges, a set of oriented faces, as I described this morning, So now we are in 3 dimensions. So vertices are so nearest neighbor edges have as boundary points vertices, pairs of vertices. The edges are boundaries of triangular faces. Faces are themselves boundaries of polyhedra. And so somehow the collection of vertex set of oriented edges, set of oriented faces, a set of oriented polyhedra forms what is called in this theory a cellular complex. So there are natural operators acting between these spaces. First of all, there is a boundary operator that given any cell in, so you see there are 0-dimensional cells, vertices, that I will denote either like this or like E naught. 1-dimensional cells that are these oriented edges. 2-dimensional cells, these oriented faces, and 3-dimensional cells that are these oriented polyhedra. Given an oriented cell with p larger than 0, there is the boundary operator, which is the operator denoted by this d, this sort of partial derivative. This is not a partial derivative. Is an operator that produces as output the set of boundary cells of C. So if you take the boundary set of a face will be the set of oriented edges on the boundary and so on, like I discussed this morning. Okay, so another natural notion that I sort of anticipated in some special cases this morning is the set of P-forms with, in our case of interest, with Dirichlet boundary conditions. This is a set of functions from these oriented cells to R3 that are odd under orientation flip. So this morning I called one forms the functions from edges to R3 that are odd under orientation flip. I can do the same for functions over oriented faces and oriented polyhedra. Vertices are not oriented, so the 0 forms are just functions over vertices. Okay, and in the following I will also let Cp with this subscript f be the lattice valued p-form. So if I consider functions that only take value in lattice vectors, vectors belonging to the FCC lattice itself rather than generically in R3, I will refer to that function as an element of the lattice valued p-forms denoted like this. Okay, so there is a notion of discrete derivative that I already introduced in some special cases this morning. So the exterior derivative is the discrete, also called exterior derivative, is a function from the p-forms to the p+1 form. So if you apply the exterior derivative to 0 forms, so a function of vertices, you produce a function on edges, as we saw this morning. So and so on. So if you apply the exterior derivatives to function on edges, you produce a function on faces, and so on. So the definition is like this. So if you take a cell in the p+1 complex, the df of C is just the sum over the boundary elements of C of f of C prime. So if you think of this in the 2 cases that I discussed this morning, so if I have a function on vertices, df of an oriented edge, remember that an oriented edge is just an ordered couple of vertices, is just Vy minus Vx. If you take a function like the slip field on edges, it's the action of D on sigma computed at the face f, as we as I discussed this morning, is the sum over the oriented edges on the boundary of the face of sigma of that edge, and so on. So if you have a function on faces, its differential is a function on the polyhedra, and is also okay. We will also need the adjoint of D, defined as usual. So you can define a scalar product among P forms as already anticipated this morning. So if you have two functions both defined on the vertex set or on the edge set, etc., you can define the standard scalar product. This will be the sum over the cells, the appropriate cells in the cells of dimension P of G1C. So it will be sum over of G1C, where the cells can be, once again, vertices, edges, faces, or polyhedra. D star is defined in the obvious way. So via, okay, this is the definition of D star. One can write explicitly the expression. I won't do it here, but it's simple. Okay, a few facts. First of all, if you apply twice the exterior derivative, you get identically zero. So we saw an example this morning. So if you take, so the example I discussed was the following. Take a sigma of this form. If you now take d sigma, this would be d squared v. This is equal to zero because as I observed, this in this case sigma xy is just vy minus vx, and if you sum now d sigma of the face of this face is just sigma xy plus sigma yz plus sigma zx, and if you plug this in, you see that this is a telescopic sum, and everybody cancels with everybody. This is general. So in general, if you apply twice the exterior derivative, you get zero. Okay. Now some standard definitions. If you have a P form whose differential is zero, one says that U is closed. If you have a P form that is the differential of a P minus 1 form, then we say that U is exact. So a sigma of this form is exact. Okay. If U is exact, thanks to this identity, then is closed. In general, as usual, it's not guaranteed that if U is closed is also exact. One has to somehow, in order to understand this, one has to understand somehow one has to discuss the invertibility of this D operator. So one has to sort of look to the zero modes. So this is where the use of Dirichlet boundary condition turns out to be particularly useful. So in the presence of Dirichlet boundary conditions, and not in the presence of periodic boundary conditions, U closed implies U exact for P equals 0, 1, 2. So this is the reason why I use Dirichlet boundary conditions. In the case of periodic boundary condition, there are some closed forms that are not exact, and so one can classify them. So it's not a big deal. One can also but one has to sort of everywhere take care of these non-trivial zero modes somehow and factor them out, treat them separately, and so we decided to use Dirichlet boundary conditions where every time we have a closed P-form, this is automatically exact. Okay, when we have a situation like this, where U closed implies U exact, then one also has this clean version of the so-called Hodge decomposition. I mean, I'm pretending I know these things, but I mean, I learned these things. So these are very standard things in homology theory. I don't know much about it, but so these are really the first basic steps. So the fact that you can, in a certain generality, discuss connect the notion of closeness, exactness, connection among the two. This kind of decomposition, Poincaré lemma, these are standard facts in homology theory. So some of you may be very familiar with this, others may not. I was not before. I'm not particularly familiar, not even now, but at least I understood this claim. So there are small proofs of this claims also in our paper, which has a section with some reminders or small reviews of these basic elements of homology theory adapted to this discrete context. So Hodge decomposition is this nice property that if you have a P-form, in this case you should choose P equal 1, 2, then you can always decompose it as a sum of on an exact part plus a non-exact part, which is the D star of something else. So there is always this decomposition. So this is a nice fact. Another thing is that in this context, the Laplacian is defined in this way as D star D plus D star, and this is invertible on the space of P forms both for P equal 1 and P equal 2. And I think also for P equal 0. For P equal 0, you should actually interpret D star as being 0. So for P equal 0, the Laplacian is just D star D. So if you write actually in coordinate, I'm always confused when I write this elegant abstract thing. So I'm always skeptical. So I of course sat down and wrote in coordinates what this means, and so you recognize it's the standard lattice Laplacian. It's just a nice way of writing it, and it's very convenient for a lot of manipulations that I think I wouldn't have been able to find out if I looked at things just in coordinates. Okay, so let me now rewrite the Ariza-Ortiz energy in using this language of differentials. I think I essentially already did it this morning, but let me redo it. And then let me manipulate this expression. I will do it in the next slides, taking advantage of this, for instance, of this Hodge decomposition. Okay, so this is just a rewriting. As I already noticed, just du of xy minus sigma of xy. So you can rewrite this as a sum over oriented edges of du minus sigma, scalar product with this matrix B, diagonal matrix in the edge space, applied again to du minus sigma. So this B is nothing but this x minus y tensor x minus y, as you see from here. So this is a projection. Remember that x minus y as modulus 1. So this is just the projection operator in the direction of the bond xy. So this B is a source of complications because this B is a projection that therefore tends to create null directions that complicate a bit things. It could be that this is an artificial, unnecessary feature of the Rizza-Ortiz model with nearest neighbor interactions. So I once discussed with Adriana Garroni, and they ended up studying, I think with Emanuele Spadaro, some related models with, I think, next to nearest neighbor interaction, in which the analog of this B had no null directions, and this may be helpful to maybe simplify something for a variant of the Rizza-Ortiz model I introduced. Okay, so this is a key proposition that I will try to explain I will try to explain the proof of. The proof is elementary once you know just a few elements of this homology theory, essentially the list of properties I discussed above. In particular, once you know the Hodge decomposition. So give an arbitrary lattice valued one form sigma, and let Q be its discrete curl. So the what I call the dislocation part of sigma, as I already mentioned this morning. So if you fix sigma, the minimum over U of the Rizza-Ortiz Hamiltonian at sigma fixed is just a function of Q, not of sigma. And it is this specific quadratic form in Q. G is explicit but relatively complicated operator. So somehow this quadratic form can be written moving the G on the left to the right using the adjoint operation. So this thing here, this G star VG, plays the role somehow of the effective, so the sort of the green function described in the two-point interaction between dislocation core and dislocation core. So this G star VG is the lattice analog of this this two-body dislocation interaction that I introduced, for instance, briefly yesterday when I mentioned the model by Kosterlitz, Taules, and company. The large distance behavior of this has exactly the same large distance behavior of the effective interaction among dislocation known in the plasticity literature. But if you want to write explicitly, this is pretty complicated, because G is complicated. It's this combination of inverse Laplacian, D star, B, D star, A minus 1, D, blah, blah, blah. A is this combination of the projection operator B I mentioned before and this star B. This A is exactly the same A that I wrote down yesterday when I discussed the harmonic approximation. So it is really exactly the same. So the Fourier symbol of this is pretty simple to write. Okay, it was very simple to write in the two-dimensional case. The three-dimensional case, you can still write the Fourier symbol quite explicitly. But the Fourier symbol, for instance, of this is quite crazy, and the Fourier symbol of this is even more crazy. So if you want to write the explicit expression of the green function describing the interaction between these locations, you can do, but the explicit expression is pretty ugly. And so once again, this is what I remember I originally started to do, so to write everything explicitly. Then I was getting crazy, and we realized with Florian that it was much better to keep things in this compact notation and play with a number of peculiar properties coming from the properties listed above on D star, the Laplacian, etc. Okay. So the minimizer is also explicit. It looks like this. And more in general, so this is, if you like, a corollary of this more general identity that allows one somehow to, you see, decompose the Rees-Ortiz Hamiltonian as a part that depends on, I would say, purely on U. It's not purely on U because you see it depends on U minus U sigma, and U sigma contains the slip field. But this is somehow just a translation. So somehow once you recenter U, this part just depends on this location. This part is called the spin wave part of the energy, and this is the dislocation part, the one that I already wrote. Okay, this proposition is really a key ingredient for our for the understanding of our theory. Is at the basis of this exact decomposition of the into spin wave excitations and dislocation excitations, as I will try to explain. So here is a small digression that I sort of already did this morning, but let me redo it because this is important. So this Q, as you see, is the key information associated with sigma. So the energy, the important part of the energy connected to sigma is encoded in this Q. So Q is called the dislocation part of sigma. Yes.
This is, G looks like some kind of pseudo inverse or something like that. So if somehow can you simplify it if you assume that E is invertible?
Yeah, I mean, yeah, if
6 are vertical, a lot of things you can't.
Yeah, so for instance, if in particular, if B where the identity, all this part would just disappear, and so yeah, the whole complication comes from the fact that B is this projection operator somehow. Yeah, things simplify. I don't think that just the invertibility of B would help so much. It is the fact that this is a non-trivial that is not proportional to the identity, I think. Okay, maybe we should discuss it on a side. Yeah, I don't think. No, so I mean, if you just use that B is invertible, which is not, you don't manage to simplify this. I mean, yeah, this starts D. I mean, you're looking at this and to this. Yeah, no, they don't really completely simplify. Okay, here I'm recalling some properties that I already discussed this morning. So, given sigma, d sigma is denoted by Q, is called the dislocation part of sigma, and is such that dq is equal to 0 for the property that d star is equal to 0. As I mentioned this morning, if you take any pair of lattice one forms which have the same dislocation part, I will call them equivalent or gauge equivalent, and you can always find a lattice zero form such that they differ by this exact form. This Q, if you look at the face, Q of that face, so the sigma of the face, can be interpreted, as I also mentioned this morning, as an elementary current flowing orthogonally to F. And if you have say a compactly supported Q, which in our case is always the case because we have the Dirichlet boundary conditions, you can decompose Q as a sum of the components, or say the maximal connected components of Q. So take the support of Q. The support of Q will be a union of maximally connected components, each of which corresponds to by definition to a certain Qi, and you can write Q as the sum of these Qi's. Now, a key fact that we will use that makes the analysis in D=3 much simpler than in D=2. That's why essentially we didn't succeed so far to treat the two-dimensional case. Is that in 3 dimension, the composition comes with the following locality property. So once you decompose Q like this, if dq, as in our case, is equal to 0, then separately all these dqi's are equal to 0. So this is not the case in 2 dimensions. This is related to the fact that somehow this function is defined on phases, which are not the maximal cellular complex in 3 dimensions. So we still have one level up. While in 2 dimensions, Q is still defined on phases, but phases are somehow the highest cellular complex, and this makes things different. So somehow in 2 dimensions, the condition that dq is equal to 0 just tells you that the total charge is equal to 0. So somehow in 2 dimensions, it's a bit like when you think about electrostatics in 2 dimensions. When you have charges, you should think of these charges like currents flowing on infinite wire across that line. The condition that dq is equal to 0 in 2 dimensions corresponds to the fact that the total charge, or if you like, the total net current is equal to 0. But this doesn't tell you that the separate components are neutral. So this was actually, in fact, a big part of the analysis of Fröhlich-Spencer of the analog model in 2 dimensions. They had to find a multi-scale decomposition of Q into somehow a convex superposition of neutral clusters, and that but this neutral cluster could be as big as you like, and this created a lot of complications. In 3 dimensions, things are much better. So because the point is that now these currents, well, in 3-dimensional space, you really have currents that now are local. Okay, so it's a matter of dimensionality. If you have, yeah, somehow this collection of, so since this is compact, this means that it's a collection of current loops. And this corresponds to the current loops that are sort of local. Okay, so this is good to be kept in mind in the following. So this decomposition and the fact that each component is separately neutral is an important point in the proof. Okay, let me go back to the proof of this proposition here. Okay. First of all, let me show you that this GQ appearing all over the places is nothing but the minimizer of this quadratic form VBV under the constraint that sorry, this should be dV. So this is the minimizer of this under the constraint that dV is equal to Q. Okay, sorry for the typo. Okay, so the minimizer can be, as usual, identified using constraint minimization. So you can introduce a Lagrange multiplier, and you find that sigma q, so the constraint minimizer, satisfies the Euler-Lagrange equation in the presence of the Lagrange multiplier, which is simply this one. So So the Euler-Lagrange equation is B applied to the minimizer equal D star lambda, where lambda is some 2 forms to be fixed in such a way that D sigma is equal to Q. Okay, how can I identify lambda and how can I construct sigma Q? Well, I know that sigma Q using the Hodge decomposition can always be written as exact part plus a D star of something. Okay, now you apply D to both sides, so this D sigma Q becomes Q, this becomes 0, and so you get the D star psi is equal to Q. Essentially the invertibility of the star operator following from the fact that also that the Laplacian, so from the property that we said that every closed form is also exact, allows one to find psi simply in this form. Okay. Now, once you know that psi is in this form, let me write sigma q as d phi to be determined plus d star d minus delta minus 1 q. And let me use the other condition following from this. So from this, it follows that if you apply d star to both sides, you get d star b sigma q equal to 0. So let me do that. So from d star sigma q equal to 0, I get, let me write it here, d star b sigma q is equal to d phi plus d star delta minus 1 q. This is equal to 0. So this means that d star bd, which is what I called A previously, applied to phi, is equal to minus d star b d star delta minus 1 q. Now, as I mentioned, this A is invertible with Dirichlet boundary conditions. So you invert and you get this formula here that defines this expression for G. Now, so I don't think you can further simplify this. It's just what you get. Okay, another observation. So this is the first thing. So this GQ that appeared everywhere in the formulas here is nothing but the constraint minimizer of this under the constraint that dV is equal to Q. Okay, other observation. If U sigma is defined like this was also one of the formulas in the proposition. If you apply the differential D both sides, you get the du sigma is equal to dd star Laplacian minus 1 sigma minus GQ. So this dd star delta minus 1, using the fact, okay, so maybe here is another point that is worth making a small digression about. So du sigma is d star Laplacian minus 1 sigma minus GQ, where this GQ it was sigma Q. Remember that the Laplacian was d star plus d star d. So this d star is nothing but the Laplacian minus d star d. So this is, well, yeah, Laplacian minus d star d. So Laplacian minus 1 is just sigma minus sigma q. And then there is this other part. Now, the Laplacian commutes both with d and with d star. So the d passes through Laplacian minus 1. This is all these magic things that you tend to not realize if you write things too much in coordinates. So the other part can be rewritten like this. Okay, but this is 0 because both d sigma and d sigma q are equal to q. So this is equal to sigma minus GQ. And thanks to this identity here and the property and the fact that sigma q is equal to GQ, we can rewrite the result is Hamiltonian this way. So add and subtract sigma q. Okay. Now you realize that using this, sigma minus sigma q is nothing but du sigma. So I rewrite this part here as d of u minus u sigma. And then we have the minus GQ. We can do it both here and here. Okay, now expand. So there will be the term quadratic in U minus U sigma, the term quadratic in Q, and then in general there should also be the cross term. So the cross term is what? Is minus, so there is a factor 2 from the fact that it's the cross term, which simplifies with the 1/2. And then we have minus GQ B du minus U sigma. Okay, I move the B this way, so I get the minus B star GQ du minus U sigma, but this is 0 for the property. Oops, no, it was here. Yeah, this can also be moved here. No, I'm doing something wrong, sorry. What do I want to say? B. Yes, but B is equal to B star. So this is D star BGQ, which is 0 for this property here. So the cross term is 0. So this the fact that sigma q is the minimizer, this is not by chance. So the fact that the sigma q is the minimizer implies via the validity of the Euler-Lagrange equation that the cross term is 0. So this is sort of standard. And this proves the decomposition that I promised. Okay, this decomposition is the key to this factorization of the correlation functions that I sort of alluded to when I said that we can separate spin wave degrees of freedom and dislocation degrees of freedom. So here I'm noticing other typos, so there should be a plus here, a plus here. So I will correct this and then send the updated version later. Okay, so remember what's our goal. We want to compute, for instance, the 1-point function, the average of the cosine. So you write the cosine as in the exponential form, and noticing that the Gibbs measure is even under appropriate parity operation. You see that the contribution of e to the plus I is equal to the contribution of e to the minus I. So you get that the average of the cosine is the same as the average of this complex exponential. So far, so good. So this is modulo some typos, the expression. Here, remember, I'm summing over the slip field, the equivalent classes of slip fields, as I mentioned, which is the same as summing over the d sigmas, as I mentioned. So every equivalence class is associated with the choice of the displacement field. Okay, and now is where the nice thing comes. So now I apply this sort of Hodge decomposition I just proved. So I rewrite this term here as this part depending only on U minus U sigma, and the part just depending on GQ, where Q is equal to D sigma. Yeah, so this D sigma, again, this is a typo. This D sigma should be Q, or okay, one should specify that Q is nothing but D sigma. Yeah, so there are some D sigmas and some Qs. I think I forgot to translate everything in terms of Q. And now you see that the two averages factor, because when you fix Q, the integral over U can be computed. You can shift. You can rename U minus U sigma. You can rename it U prime. And you get that the average of this part and this part is given by this measure here, and the average of this part, and this part is performed using this weight here. Okay, so the sort of the spin wave dislocation decomposition at the level of the energy implies this spin wave dislocation decomposition at the level of the Gibbs measure. This is magic. I mean, this is very specific of this quadratic model. So again, this is somehow the same as in the case of the Villain model in the context of the theory of rotator model. So somehow in the Villain model, things are a little simpler, but once you understand that, then you can also understand the XY model. In a famous paper by Frelick Spencer on the Kosterlitz-Towles phase in the low temperature XY model, they simultaneously treat with the same method the Villain model and the XY model. The analysis of the Villain model is a little simpler, but the one of the XY model, for which you don't have, so for the Villain model you have exactly the same analogous decomposition factorization at the level of Gibbs measure. You don't have it for the XY model, but once you understand this, I mean, there are additional technical complications, but morally things work. I mean, I'm not sure that this would be as easy in this context, but okay, this is at least the hope. Okay, now you see, the spin wave part now is a Gaussian computation. So the spin wave part is something you can compute explicitly, and the only non-trivial part is the dislocation part. So let me focus for a second on the spin wave part. Okay, you see, the spin wave contribution to the correlation function we're interested in is given by this Gaussian integral. You compute it just, if you like, completing the square at the exponent, and you get an expression that is essentially the same as what we encountered yesterday in the harmonic model. So we get the exponential of, so this was exactly the expression we encountered yesterday downstairs when we were in the harmonic model. We were computing the expectation of the quadratic, the expectation of the quadratic displacement. So you get integral decay of a to the minus 1. Yes?
So it might be very nice, but just forward. So we are trying to see the competition between the formation and introducing the dislocation.
Yeah, in this model, what happens is
some non-local effect.
Yeah, but the non-local effect somehow factor out.
The models to integrate and put it aside.
Yeah, the spin wave somehow it becomes. So you see, you get the quadratic part shifted by something that depends on sigma. But once you integrate out the sigma dependent shift plays no role. So you essentially you get a perfectly elastic harmonic model on top of this sigma profile, which plays the role of the nu zero.
Like that, it would be a major difficulty to.
Yeah, okay, it will be a difficulty. Yeah, I don't know how major. This was whether it's major or not. This was essentially the comment I just finished on the Frelick Spencer paper. So once again, that I think it's. Yeah, in 3 dimensions, it should not be a major difficulty. In 2 dimensions, it's a difficulty, but at the end, somehow the main difficulty is to understand this dislocation part, the truth. Once you understand well the dislocation part, a possible coupling between the spin wave and the dislocation degrees of freedom is not the worst part. Say it again?
You can this dislocation part more local, and you can.
No, it's not local. It's not local at all. No. This is this decays like Coulomb. This G star BG is like a Coulomb interaction. The point is that here we are decoupling completely somehow. You should always imagine that there are this dislocation. So think in the picture, so physically, think about the grain picture I showed yesterday. So you have these locations that roughly correspond to the fact that somewhere there are these geometric defects. And in the complement of this, of where you have this location, you have almost perfect crystal. It's not really perfect, so you can have sort of harmonic compression and deformation. The point is that in this specific model, this compression, you can integrate out, it's just a harmonic thing, is this contribution here. And you're only left with the non-local effect of the dislocations. In real life, they don't decouple, but they are coupled. But morally, the idea is that, okay, first of all, as usual, it's better to start in a situation in which you have, but morally, I think that once you understand well this part, in a situation where you have coupling between sort of these elastic degrees of freedom and the dislocation, the coupling should not be the worst part. So once you have a good control of the dislocation part, the coupling should be okay. But this, of course, is philosophical. Then you have to do it, and but this is what I believe. Okay, so once again, the spin wave part is explicit and allows you to allows one to compute explicitly the contribution to the correlation part of coming from these elastic deformations. This is exponential of d3k, because we are in 3 dimensions, over k squared, because a of k, if you remember, behaves like k squared small k. It's exactly the same ak that I was introducing yesterday. It's this operator here, which is this, if you remember, yesterday I was computing exactly this. It was this Laplacian weighted with these projections over the nearest neighbor direction. It's exactly this thing here. And you can write the Fourier symbol and realize that at small k, the eigenvalues scale like k squared. So this is more like d3k over k squared, which is finite in 3 dimensions. And once again, in 2 dimensions would give you a log divergence that is a major issue in 2 dimensions. Okay, so this is good. Now we're left with this part. So the goal now, so actually this part, now the goal is to get a lower bound on this part, which doesn't change. So the result will be e to the minus c0 over beta times this contribution that I want to get the lower bound on. Okay, so this is the content of the last part of this lecture. This is this part of the analysis closely follows Fröhlich-Spencer 82. So somehow Fröhlich-Spencer in 81-82 wrote these 2 amazing papers. The first one in 81 about this paper I already mentioned many times about the behavior, the Kosterlitz-Tauler space in the Villain model and the XY model at low temperatures. And then the next, the following year, they used essentially the same method to prove, say, among other things, that the rotator model in 3 dimensions as spontaneous magnetization. And they actually did things, so strangely enough, they did things in the wrong order. So the 2-dimensional case is very difficult, and they had to do this multi-scale decomposition over neutral clusters, blah, blah, blah. But the same method applied to 3 dimensions was much easier, but they realized it the year after. So the year after they wrote this other paper on the 3-dimensional case, logically, it would have been more linear to first do the 3-dimensional case, which is easier, and then which does not require multi-scale analysis, and then go to the multi-scale analysis in 2D. But somehow, historically, they were first worried about the more serious problem, and then to the easier problem. So here we are sort of doing this easier part. following the same strategy of Frelich-Spencer 82. And in some aspect of the proof, a related result by Kennedy and King in 86. Okay, the strategy is the following. So this is the average we want to compute. So there is the observable is e to the I h GQ. Remember, h was this function over edges that was equal to V0 on the path from x to x external and 0 otherwise. So is a function supported on this path. G is this complicated operator written somewhere. And this is the part coming from the local energy of the dislocation course. Okay, so we do the following. So, first a preliminary sort of aesthetical rewriting. So I split this part in two. One I keep on a side, the other I combine with this guy. So I think of this as this local weight, then e to the minus beta over 2, this quadratic form, and then the observable. Okay, now we use the so-called Sine-Gordon transformation. So we write this in a local form as far as Q is concerned, at the cost of introducing an auxiliary Gaussian field. So I write this as the average over a Gaussian field of e to the iq phi. The Gaussian field has covariance equal to beta G star Bg plus W. Okay, the presence of this W0 that was at the basis of this rewriting here is necessary in order to guarantee that the covariance is strictly positive. So if you didn't have this term, this would be non-negative definite, but there are some null directions associated with this projection operator B. So it's easy to see that there are some null direction for this guy. So if we want this to be a positive operator that is required in order to use this identity, it's better to keep some part of this local weight here. Okay. Okay, so we rewrite this in this way. And this, you see, allows one to, so this part is local because it's just the sum over all phases of Q squared F. This is also local in Q. So you see that at the cost of having introduced this extra averaging, we now have something that is local in Q. And so we bring this sum over Q in, so we sort of exchange the sum over Q and this Gaussian average, and then we decompose this sum over Q in we sort of distinguish contribution with different supports. So here I'm summing over all possible Qs, allowed Qs. Here every given Q has certain support. I'm now exchange the sums between the choice of the support and the choice of Q. So I'm summing over all possible supports of Q, and then I'm summing over the Qs with that specific support. Okay, so far nothing very serious. Now I use the magic property I told you before. So if Q if I now decompose Q as a union, the support of Q as a union of maximally connected components, each component has each component Qi has dQi equal to 0. So if you now write here Q as a sum of the Qi's, everything factorizes. So you get this decomposition over connected components, so you can rewrite it like this. So you can write as a sum over disconnected axes of the product of the case. These are I'm trying to set up things in a way that for those of you who know cluster expansion is appropriate for doing cluster expansion. So the condition that the xi's are disconnected is encoded in this function. I know I'm always using the same symbols, but whatever. So this is a function that enforces the fact that these supports of the maximally connected component are in fact disjoint among each other. Okay, here is the magic of the first whatever Meyer expansion, cluster expansion. So the sum of this thing is equal to the exponential of a very similar sum, modulo the fact that this exclusion function here is replaced by this function here, which is called the Ursel function or Meyer function. Sorry, this is 1. This is a typo. Phi t of x1 is equal to 1, and phi t of a collection of connected component is equal to an explicit factor. An important feature of this explicit factor is that this is non-zero only if x1, x2, xn form overall a connected group of. So this is why this is called cluster expansion. So once you exponentiate, the resulting, so you start downstairs with a collection of disconnected pieces. Once you exponentiate, you get a similar thing, but with the new function that now enforces connection rather than the one we started from that enforces disconnection. So this is a magical fact if you never saw it, but it's very standard. So this is combinatorial lemma. So as long as you don't worry about convergence of this series, this is just a combinatorial lemma, non-trivial, but just combinatorials. Of course, this makes sense if this summation is convergent. And okay, so in order for being convergent, you need some bounds on these activities. In our case, you see, in order to get bound on k, you just drop this part here, and you just you have to sum over these exponentially small factors, and it's very easy to see that once you fix the support, this activity is smaller than is exponentially small in the support. So this is very easy. I mean, it's really an exercise. Okay, now another standard fact. If you have a summation like this, which is standard in cluster expansion, with an activity that is exponentially small, this summation is exponentially convergent. This is also very standard. So now you resum this, and you get this very simple expression where the coefficient is, if you like, the sum of the cluster expansion. So I sort of reconstruct. Remember that each of these factors has e to the iq1 phi plus g star h, e to the iqn, blah, blah, blah. So you can always extract from the product of this factor an overall e to the iq phi plus g star h, where q is the sum over all the qi's. I'm sort of undoing the decomposition just at the level of this prefactor. So somehow this prefactor, I keep it all together here, and all the other combinatorial factors are summed using this Ursel function. This sum, as I told you, is convergent thanks to very standard lemma in cluster expansion that you can find in many books, and the result is that the sum not only is convergent but is exponentially small. Good. Okay, so you see, you now have average of exponential of this summation when you have this exponentially small coefficients times this exponential. Okay, you should resist 3 more slides. I wrote so these formulas are long because I tried to write all the details. So they are less scary than it looks. So the first step is really elementary. I'm just rewriting using once again the evenness in phi and in q of these measures. I'm using that this e to the iq phi plus g star h can be replaced by the cosine. So this is the cosine of q dot phi plus G star H. And now the cosine of Q phi plus Q G star H, I use the cosine of the sum equal to cosine cosine minus sine sine. So nothing very deep, okay? So this is cosine cosine minus sine sine. So this is not scary. Okay, so let me now isolate. So I want to isolate the dependence upon H. Remember that this is a rewriting of the numerator. So we want to evaluate this H-dependent partition function divided by the H equals 0 counterpart. So the correlation function we want to evaluate is a ratio of this Z of H divided by Z of 0, okay? So I have the ratio, okay, so this is a typo, this should be 0, sorry. So down in the denominator, I have the same expression with H equal to 0. So this is replaced by 1, and this is replaced by 0. So let me, in the exponent, add and subtract the part with just the cosine, the one that would appear in the denominator, so that I can rewrite the ratio in this form. So I have e to the minus this thing. So here, instead of cosine, I have 1 minus cosine, and here I have this part here. What is this m beta? Is just the new measure obtained by dressing the Gaussian measure by this cosine part. It is the measure that you have at the denominator, okay? Yeah, so this thing here at the denominator is just a compact way of rewriting the denominator that would be the thing with H equals 0. Okay, so written like this, you see that this ratio, the correlation function we want to compute, is the average with respect to this now non-Gaussian measure of this exponential. Okay, now magic. So here there are some magic steps that I learned from Felix Spencer and Kennedy and King. This is, I think, all very, very nice. So here you use, for the purpose of a lower bound, that is what we need, we use Jensen's inequality. So the average of the exponential is larger or equal than the exponential of the average. Now, since this measure is even in phi, the average of this is 0, and you're left only with the average of the cosine. So for the purpose of a lower bound, we just bound the average of the cosine by 1. And in this way, we drop completely the averaging. So we dropped phi. This is, again, magic. I mean, this is Jensen's inequality plus cosine smaller or equal than 1, and we obtained a complete disappearance of the auxiliary Sine-Gordon field. Okay, and now we are left with bounding this thing. So this is straightforward, but it's not completely trivial. Okay, first thing we want to do, we want to, for the purpose of a lower bound, replace 1 minus cosine by a quadratic form in Q. This is fine. Okay, the most naive thing would be to replace this by QG star H squared. But this is not very good because QG star H is not typically small. I want essentially to replace this by this modulo 2 pi, choosing the modulo 2 pi in an appropriate way so that the resulting thing is small. So for this purpose, we need to appeal to a version of Poincaré lemma due, in the form we used it, due to Kennedy and King. So it is a sort of constructive version of Poincaré lemma. So we know that Q is a lattice 2 form, such that that is closed. So as usual, if it's closed, it's exact. So there is some. So you can always find some 3 form. No, some 1 form such that Q is equal to dg. Okay, but if you don't do things, so, and actually, since Q is a lattice valued form, G can be also chosen lattice value. This is, you have to think about it, but this is also true. Now, we need some control on this G, and this is what is the content of this lemma due to Kennedy and King. So they really show the procedure to construct an explicit G that they called N of Q. So they showed that, well, they showed it in a slightly different context, but you can really follow the same proof line by line. So they showed that the support of this G that they call NQ here is not so different from the support of Q. So they in their construction they can choose the support of this NQ to be the smallest parallelepiped containing the support of Q. So if the support of Q is here, this is B of Q, and they have that the support of the NQ. So the support of the NQ is this one, and also they have some control on the sup of this. So it cannot be too big. So if Q is small, also NQ is small. Remember that Q is lattice valued, so small, whatever. So if it's not too big, this is also not too big. You lose a little bit, so you have this power 4, but this power 4 is not very important. So this power 4 is killed by the exponentially small term that we gained. So remember that Z, so this small z here, is exponentially small. So this beats any power. So you can allow powers without. Okay, so now we rewrite this. So Q is rewritten as D and Q, and G star H is written using the definition of G. So I remind you that G, G star, okay, maybe I don't remind, it's written here. So G star, which is the adjoint of G, is this ugly combination here. It's very ugly, but you shouldn't get scared because by manipulating these D stars, etc., you get something much simpler than what you would initially suspect. So take into account that these complications are among the new complications that the paper of Bauer, Schmidt and company don't have. So we have this structure that is related, I think, to the microscopic definition of the model, which is, from my perspective, closer to realistic description of microscopic elasticity models. They essentially replace all this by operators that are the standard green function on the lattice, losing somewhat these projection operators and these details that I think are important for the description, for a realistic description of these locations. Anyway, so you get you get this. Now you do the same trick as I did before. So this D star D is written as Laplacian minus DD star. So there is a part. So I do exactly this thing here. So D star D is written as Laplacian minus DD star. And if you do so, you have the contribution from the Laplacian, in which Laplacian minus 1 is equal to 1. And so you get NQ times this part. So you have NQ times H, which comes from this 1. And then you have NQ minus NQ times this part. Okay? And then you have the part in which you have, sorry, there is another typo. This is minus NQ DD star, blah, blah, blah. Okay, now magic thing is that this part here is 0. So this is the magic. Yeah, I remember when we realized this, we were sort of happy. So you have NQ, well, you have this D star, Laplacian minus 1, 1 minus B, D, A minus 1, D star, H. So this looks scary, But once again, so Laplacian commutes both with D and D star. So you can move the D star inside. Okay, now you see that you get D star H minus blah, blah, blah D star H. So you can factor D star H out. And you get 1 minus B D, sorry, D star B D A minus 1, period. Okay, this is, I think, a cancellation similar to the one you wanted to do before. So now this is equal to A. So this is A minus 1, which is 1. So this is 0. So this part here is 0. This part here, since NQ is lattice valued, H is reciprocal lattice valued, this is proportional to an integer multiple. So this is an integer multiple of 2 pi. So this is 0. This can be dropped for the purpose of computing the cosine. And so we are left with cosine of just NQ times this ugly thing here. So this ugly thing here is called epsilon, just not to be, because it will come. Okay. So I hope I convinced you that, I mean, these steps are all sort of elementary. Maybe you're getting a bit lost, but if you are interested and you have the patience to read through these notes, it's very easy. I mean, so you get now this 1 minus cosine of this epsilon and q, and now we do the trivial bound that 1 minus cosine is smaller or equal than the argument of the cosine squared over 2. And now, so we finally have a lower bound in terms of an exponential of a quadratic form. So now we are done. So this the goal somehow is to go from this to so the final goal is to get something like the square norm of epsilon. To get there, we have essentially to write this as a convolution epsilon kernel epsilon, and then use the fact that the kernel is exponentially decaying, and use Young's inequality to write this convolution as the L2 norm times the L1 norm of the kernel. So this is the goal. So for this purpose, we proceed like this. So remember that NQ is bounded by Q to the 4 and as finite support. So we can always write this in this sort of trivial way. There is the square of the sup of NQ times the double sum of epsilon over the support of NQ. So nothing very deep. The point is that the exponential decay of Z will help us. So if you now you now plug this in and you exchange the sum over E prime with the sum over Q. You use the fact that Z is exponentially small to obtain a rewriting of this quadratic form in the following way. So you have sum over E prime of epsilon E prime times a kernel that is exponentially decaying. So this is what I promised. Once again, this summation can be performed well, just using this is really elementary, following from the exponential decay of small z. Okay, so we ended up with this expression where so we ended up with this expression, and now I use Young's inequality. So this can be seen as a convolution of epsilon with this kernel that is exponentially small. So I use Young's inequality, Young's convolution inequality, and I I further bound this, this by the L2 norm of epsilon times the L1 norm of the kernel. The L1 norm of the kernel is exponentially small in beta. So it's summable and is exponentially small in beta. So at the end of the day, I get e to the minus L2 norm of epsilon times an exponentially small correction. Good. Now, what is the L2 norm of epsilon? This is again magic using these expressions. So remember that epsilon was this b d a minus 1 d star h. So epsilon epsilon is b d a minus 1 d star h scalar product with itself. D a minus 1 d star h. So I now use, there is something, yeah. So I now move this using the usual rules. So B is self-adjoint, so I get a B squared, but B is a projection operator, so B squared is equal to B. Then I get D star. Then I get a to the minus 1, and I stop here. This is equal to A, so this and this simplify, and I get this thing here. Now, remember that H was introduced earlier to write U V0. So if you remember, Ux V0 was rewritten as H comma du. So D star H is nothing but V0 times the delta function at x. So this is nothing but V0 a minus 1 xx V0, and this is nothing but the same Fourier integral that we already encountered in the spin wave approximation. So this thing here is exactly the same as this integral here. Exactly the same. So we obtain, after all those manipulations, we obtain a lower bound of the form e to the minus constant depending on beta times exactly the same integral. So the resulting lower bound we obtained on our correlation function is of the form e to the minus 1 over 2 beta this integral that is what I called C0 times e to the minus C beta same integral. So this means that the lower bound is of the form e to the minus C0 1 over 2 beta plus this constant C of beta. But this constant C of beta is exponentially small. So the contribution from the dislocations is just an exponentially small correction to the 1 over beta. And then this looks, I mean, most of the steps I showed really are due to Frelick-Spencer. There are some complications due to the presence of all these strange operators. I remember trying to mimic the strategy of Frelick-Spencer, starting to bound these terms, and I was getting nowhere, because as soon as you bound things, you get lost. But if you keep things with the right structure of this D stars B, you see that at the end, magically everything combines in the good way. So this implies the desired estimate and concludes the proof. Now we have a lot of open problems. Many of them I already mentioned, so it would be nice to prove screening at high temperature. In 2 dimensions, it would be nice to prove orientational long-range order for an appropriate observable testing breaking of linearized rotational invariance. It would be nice to prove 2-dimensional algebraic decay of positional correlation at low temperatures. Another subject that I didn't have time to enter, and I'm sorry because I think this was maybe more of interest for some of you, is clarify better the connection with physics of grains. So yesterday I mentioned this was originally an optimistic plan to also discuss something about the Reed-Shockley law in our context. I don't have time to do it today, but please look at the paper with Florian. I mean, we made a number of discussions. So there are actually, I realized it tonight, last night, rereading our paper. So there is a very long discussion, essentially about the point raised in your question yesterday. So what's essentially what's the connection between the location of these locations and the rotation angles? This is not a priori obvious. So the description I gave today, it's clear. So technically, the most convenient thing is to think in terms of these Qs, these D sigmas. Now the question is, given a pattern of these charges, of this dislocation course, can you reconstruct somehow the pattern of orientations? In particular, is there a way to identify grains sort of equivalently, both in terms of distribution of dislocations and in terms of angles, relative angles of orientation? Okay, this is not obvious. We have a discussion in our paper, which is quite lengthy, because we actually propose a way to pass from angles to dislocations and vice versa. But our discussion is not resolutive. I mean, we make some computation in some simple geometries, but similarly to the question you asked today, it remains to be seen if in general, given a certain pattern of dislocation, you can infer the corresponding angles and vice versa. This is something, again, a subject that would be very interesting to try to connect this model. It's in particular, it's low temperature behavior with a mesoscopic model of grains. In particular, is it true that typically at low temperature you form grains? If so, are these grains rotated one with respect to each other, typically with these magic angles in the Reed-Shockley law? These, I think, are hard questions, but we are not able to answer these hard questions in this simple model. It's unlikely we can do much better in more realistic ones. And I think that's more than enough.